Hey man, Uranus is weird.
What? Yeah, Uranus doesn't act as it should. Well, I mean, sometimes when I eat cheese, it gets a little,
What does that have to do with planets?
What? The planet Uranus doesn't orbit the way you would expect with Newton's laws, so I'm concerned that Newton's laws are a bit flawed.
Oh, yeah, the planets. Yeah, interesting. Yeah, mm-hmm.
Wait, so when we went for cheesy nachos the other day,
Never mind. Okay, orbits. Yeah, so, well, maybe there's some other big mass out there that's like pulling it in a weird way.
well, it'd have to be pretty big, like a planet, and I don't see any other planets out there.
Well, based on its orbit, we could calculate that there'd need to be something about divide by this, carry the 2, square that. It'd have to be about right there. Aim your telescope there.
Well, there it is.
That interaction is based on how Neptune was actually discovered. It wasn't seen first in the sky, it was calculated based off how orbits were changed around it. And I mention that because it's interesting, but also because that's how we strengthen our confidence in scientific ideas. They don't just match what we've already observed, they can predict things that we're going to observe. And another thing that strengthens scientific theories and ideas is when it aligns with previous understanding or ideas. And I mention that because in this video, we're going to look at Kepler and how his 3 laws of planetary motion line up with Newton's universal law of gravitation that came over 50 years later. So in this video, we're going to look at Kepler's 3 laws of motion, focusing mostly on his third, where we do calculations with period and radius. So let's take a look at Kepler's 3 laws of planetary motion. Kepler was an extremely intelligent and curious mathematician, and he dedicated most of his life to trying to understand what he described as the order of how the planets and the stars worked. And he played around with different ideas of different orbits, different shapes, even different musical tones of how the planets all moved. He's famously known for his 3 laws of planetary motion, so let's take a look at those 3, starting with the first one, which is elliptical orbits. Saying that planets don't go in a perfect circle, they go in an ellipse. And what's an ellipse? An ellipse is a closed, oval-shaped curve in a plane where the sum of the distances of any point on the curve to 2 fixed points, the foci, are constant. That's a little bit tough to understand. Let's see what this means. Well, we're talking about orbits, and this would be a circular orbit. The blue dot is orbiting around the yellow one, but he said they're not perfectly circular like that. He said it's a little bit squished circle, kind of looking like this. And mathematically, looking at an ellipse, there's these 2 points kind of in the middle. They're called the foci. So it's saying the definition of an ellipse. I haven't drawn it perfectly here, but you'll get the idea. If I take a point, and we're considering this to be a planet going in an orbit like this, if I take the distance from the planet to each of those 2 foci, I'm going to add those 2 numbers together. And then if I consider the planet in another position, say this one here, and I measure the distance between the planet and the 2 foci, if I add up the initial ones, the red and the yellow line, I get a certain total distance. And then if I add up the white and the purple line, I should get the exact same distance. So as I move closer to one, I move further away from the other, and it ends up giving me the same total distance from the foci. So basically all we got to know, it's not a perfect circle, it's a bit of a squished circle like an ellipse, and this is how he said the planets are going to be orbiting in this squished kind of elliptical shape. Now, not all of them are going to be this drastic. This is definitely exaggerated for the point of showing the shape. But when we notice it go around here, something that's important is we can see that over here, I put these little markers to show how fast it's moving, and they're pretty close on this side here because it's moving fairly slow. But then as it goes over here closer to what it's orbiting, the dots are further apart to show that it's going faster. So we say it's going fast over here in its orbit and slower over here in its orbit. And that makes sense because where it's going fast over there, the distance to the object it's going around is small. And we saw in previous lessons when it gets closer to a heavy object, the field strength is stronger. It's going to feel a larger gravitational force. So it gets whipped around that side. But when it comes over here and the distance is much larger, it's going to be traveling much slower. And this leads well into his second law, which is his law of equal areas. So how this works, it says the area of an ellipse covered is the same for any consistent time interval. Again, tough with words, let's show what this looks like. So I'm going to imagine the planet right in this point. We're going to say to right there. I'm going to draw a line from the thing it's orbiting, imagine it's like the sun, to this object that's orbiting it. And then we're going to wait a certain time period. Let's just say 20 days to make a nice number. And in 20 days, it orbits from there to there. Okay, now I'm going to draw a line to that point and shade in the area, the amount of the ellipse that it covered. Let's call that area 1. Okay, now let's take another point in its orbit. We're going to go over to the far side there at this location. And we're going to wait the same amount of times, that same 20 days now. But because it's going faster, it's going to travel a larger part of that curve. And now we're going to put in our line and shade in this area. We're going to call that area 2. Kepler was a very good mathematician. He got some real good data, and he was able to compare these, and he said the area of one is equal to the area of another. Isn't that kind of crazy? With this pattern, if it covers it in the same amount of time, the area of the ellipse that it covered is exactly identical. And you can do it here. You can do it for any section on the ellipse. The area that it covers is equal as long as we're waiting the same amount of time period during that orbit. And that idea of slow and fast also plays into his third law here, which is called the law of periods. Period is the time to make one lap or one rotation in its orbit. So I'm going to compare these two green and blue planets. They're just kind of made up and going at the speed here. But we can see that the green one is going significantly faster for the same reason that we said before. It's closer to the thing that it's orbiting. The blue one's further away, so it's going to be traveling significantly slower. And Kepler, again, a really good mathematician, always looking for patterns and order. He says, let's consider the time it takes for that to go around, which we're calling the period. I'm going to put that as the period of the blue planet, or mass in this case. And I put it as a big T because it's going to take a lot of time for it to go around because it's further away. The green one is going to be a smaller period because it doesn't take as long to go around. It's going to go around in less time. Let's then consider the distances. Well, I'm going to put the radius here, how far it is from the thing it's orbiting. It's pretty far. It's a big radius to go to the blue one, but a smaller one to go to the green one. So bigger radius, bigger period, or bigger time. What if we could set this up in a ratio? So I don't know how he does this. He finds this pattern where he says, if I could take t squared over r cubed, I get a number. Let's compare that to the green one, and they're exactly equal. If you square the time that it takes to go around and divide by the radius cubed, they end up giving you the exact same number. And it doesn't only work for just these ones. It could work for anything going around. Let's say we take another one. It's closer. It's going really fast. So it's got a really small time, but a really small radius. We plug that in. It's equal as well. Anything going around the same thing is going to have the same ratio of period squared over radius cubed. And this was a constant for anything as long as it's orbiting that yellow dot in the middle. Anything orbiting that dot got a number, and he called this Kepler's constant. The constant number for that yellow thing, anything orbiting around it, is its time squared over its radius cubed. And that's all well and good. It's a very cool pattern that he found. But years later, Newton started learning more about gravity, and we want to figure out, does Newton's law of gravitation agree with this that Kepler found? Well, let's take a look. Newton's is g m1 m2 over r squared is the force of gravity. And Kepler says you get this constant number with the period squared divided by the radius cubed. It's hard to tell if they're the same thing at this point because they look so different. So we're going to do some rearrangements to try and see if we could see if these relate to each other whatsoever. And the first thing to start here is saying, well, if I have an object going around in a circle, we're covering this topic because we're talking about centripetal force. That's what this chapter is. So we got to work centripetal force in there somehow. So let's say that the force of gravity pulling the orbiting object to the center of the circle is equal to Fc. So we have some equations for Fc. So let's start with that. Fc is equal to mv squared over r. So gm1 m2 over r squared is equal to mv squared over r. And I like this first step because there's already so many things that are the same on both sides, we can do some canceling. So this mass right here, that's the mass of the thing going around, which we'll call the planet that's orbiting a star. I can cancel out the mass of the planet over here as well. So let's get rid of that mass. And then I see a radius, the distance to the center of the circle and the distance to the other planet. So we can, or the star, we can cancel that out. So that's nice. We've already got lots of things canceled out. Let's simplify this. GMS, the mass source, over radius is equal to velocity squared. We did some good math there, but it still doesn't really look the same. Let's do some more math here. Well, V is equal to d over t. We saw that early on in the course. And the distance that it's going to cover when it's going around in an orbit is going to be the distance on the outside of that circle. So as it's spinning like this, the distance that it's going to cover to make one lap is going to be the circumference, which is calculated with 2 pi r. So let's take that distance, plug in 2 pi r for that distance. Okay, this is good because now I have t where I didn't have t before. In this equation, I do have it in Kepler's. So let's see if I can put this into newtons, but I see I got to sub in for a v squared. So let's square this side, which means I have to square this side as well. Okay, let's just simplify this. So 2 squared would be 4 pi squared r squared over t squared. It'll look a little bit like this. V squared is 4 pi squared r squared over t squared. So now if that's what equal to v squared, I can sub that in for where I see v squared. Let's do that. Plug it in there. Okay, there's a lot of things going on there. Let's see if we can simplify this one. Okay, this is where we're at so far. So what I notice again is there's some things that are similar, mostly the r's. I have an r squared here and an r over there. Let's bring those together. I'm going to divide the r down. Okay, that's good. I get my r's on the bottom, just like Kepler had the r's on the bottom. Well, Kepler had t's on the top, so let's move my t's to the top and pull GMS down to the bottom, switch those two out, and that's actually looking pretty similar. I have 2 t's on top, t squared, 3 r's on the bottom, r cubed. And this part looking very similar to what we have for Kepler's. Kepler said that t squared over r cubed should give you a constant value. We have a mess here, 4 pi squared over GMS. Is that a constant number? Well, let's see, 4, that doesn't change. Pi squared, that doesn't change. G is a constant. Mass source, that's the thing we're going around. He said this number is calculated for going around the same one thing. That gives us a constant number. So that could give you a value of k, and these actually do agree, even though they look like they're kind of completely different formulas, and Newton's was developed over 50 years later, they actually match, which gives us more confidence in this is how we can describe how orbits work. Now you might be thinking, yeah, that's cool, but what kind of questions do I actually solve with this? Okay, this is when we're going to use that equation. When we know 2 things are orbiting the same thing, my green and my blue one, I know if 2 things are orbiting the same thing, I can figure out the ratio of the period to go around, the time, and the distance from the center. So this is when you're going to use Kepler's equation, whenever you know 2 things going around the same thing. All right, the time is time to complete one orbit there, that's period. And we're going to look at the radius and the radius there, compare those two. Now I do notice that when you draw that there, well, the radius is different because it's an ellipse. When it gets closer, the radius is going to be different. We're going to use the orbital from our data sheet, which gives you the average. Because you're right, sometimes it's closer, sometimes it's further because it's elliptical orbit, but we're just using the average to figure out the period. So let's take a look at an example. This one says, how many days does it take Mars to orbit the sun? Okay, we can use Kepler's equations here because I know 2 things that are going around the sun. I know Mars is going around the sun, and nice, I know information about Earth going around the sun as well. So 2 things are orbiting with the same thing. I can use Kepler's equation of t squared over r cubed is equal to t squared over r cubed. I put the blue one for Earth, like a red one for Mars. I'm trying to solve for the time. How many days does it take Mars to orbit the sun? So we're going to rearrange here for t. I'm going to multiply the r cubed up, and then I just got to take a square root to get the time for Mars by itself. So I square root, and we're ready to go. We're ready to plug into our equation. Not too bad. A little bit of big numbers here. For the time, I'm going to put 365 days for Earth. I know it'd be 365.25 because of leap years and stuff, but generally it's accepted okay if you just put in 365. You should get close enough to select the right answer on a multiple choice test. Next, I put in the radius for Mars. This is the distance from Mars to the sun. Its orbital radius of the sun is 2.3 times 10 to the 11. And then to the Earth's orbital radius, 1.5 times 10 to the 11. Let's enter this in our calculator because that's a big point of mistake here, entering it incorrectly. So I'm going to start with the 365 squared times 2.3 times 10 to the 11. Put that in brackets, cube that value to the 3, and I'm going to hit enter, get our number at that point. Okay, next I'm going to divide by 1.5 times 10 to the 11 cubed. Put that number in brackets and cube it. Make sure we divide by that number cubed. Hit answer and see where we're at. Now I've done everything under the square root. My last step is going to be hit square root, answer, and I get my number of 693 days. That's a pretty long time. It takes 365 for Earth to go around. Mars is going to take more than 693 days to go around. Now, there are some small inaccuracies here due to these numbers being rounded and the 365 being off, but it's pretty close to 693. And that actually makes sense because Earth is closer to the sun. So we said it's going faster. Mars further away should be going slower, and it's traveling a bigger curve. So it makes sense that Mars would take more time to go around. And that's a perfectly good way of doing it, but I'm going to introduce another way because this is some really big distances, like 1.5 times 10 to the 11 meters is really big. Space is so big that it doesn't really make sense to measure things with meters. A meter stick is not that big. So to measure space with it, we can make a better unit. I'm going to just take Earth to the sun, and I'm going to call that 1. Just like I have 1 meter was about this big, I'm going to call Earth to sun, and that's 1. And I need a name for the unit. We're going to call it an astronomical unit. And I'm actually not the person coming up with this. This is a real thing. An astronomical unit is the distance from the Earth to the sun, and we use that as our new kind of meter stick to measure things out in space. Okay, so I can say that the sun to Mars is 1.54 astronomical units if 1 astronomical unit is sun to the Earth. And the reason why this is useful is because when I'm putting into Kepler's equation, I could have any units as long as they're the same. So my time could be in days, hours, years, seconds even if I want to, as long as it's the same for both planets. My distance could be in centimeters, meters, kilometers, or astronomical units. This is going to make it a lot easier in our calculator because we're going to have the same equation, rearranged the same way, square root, and we plug in, I have the 365 days because I'm going to get an answer in days, so those units are the same. Then I put in 1.54 astronomical units and 1 up here astronomical unit for Earth. That makes it a lot easier entering the calculator. 1.54 cubed times 365 squared to get my answer. Divide by 1. Divide by 1 cubed. I don't have to do anything there. Dividing by 1 keeps it the same. Square root, and I get an answer. It is a little bit off because these numbers are a bit rounded, but 698 days. Again, small inaccuracies due to my rounding of these astronomical units, but you basically get the same answer. So now going into our last question, this one says, Halley's Comet orbits the sun every 76 years. What's the average orbital radius in astronomical units? Okay, so Halley's Comet has a very cool orbit because it's very elliptical. It takes 7 years to do this big ellipse, and this probably isn't even to scale. I'm just using it for a diagram. But it spends most of its time out here going very, very slow, slowly falling towards the sun, whips around it really fast, and then comes out and spends most of the time far away from the sun. So we're not going to see it for a long time, at least from when this video is being made. But we're going to try and calculate the average distance to the sun, because sometimes it's very close, sometimes very far. We're going to try and calculate the average with Kepler's laws, which does take into account average radius. So I throw up the formula. In this case, I have the blue one as being Halley's Comet, and the green one is Earth. We're going to rearrange for the r, that is Halley's Comet, the radius for Halley's Comet, but I have an r cubed there. How do I get rid of a cube? Well, to get rid of a square was a square root. To get rid of a cube, it's actually a cube root. So I got to throw a little 3 up top there. It's in your calculator when I hit math. We'll see that in just a moment. Okay, now we go to plug into these values. I got 76 years, so I should put in the orbital period of Earth in years, and it's asking for AU, so I got to use Earth's distance in AUs. And this actually becomes pretty nice because 76 years squared divided by the years for Earth to go around, 1. That's what a year is, the time that Earth takes to go around the sun. So divide by 1 squared. What's 1 squared? 1 times 1 is 1. So I don't even have to worry about that squared. That's just the number 1. And then the number of astronomical units that Earth is from the sun, that's the definition of an astronomical unit. It's just 1. And 1 cubed, 1 times 1 times 1 is just 1. And then one more time, 1 divided by 1 is 1. So we don't have to do anything with these numbers over here. We just have 76 squared cube root to get our answer, and we get an answer of 18 astronomical units. Again, some small inaccuracies due to rounding. And that's all we have for this video. So it was a bit of a longer one. I know a little bit complex, but I hope it helped you to understand his first 2 laws and understand how to calculate his 3rd law of periods. If you found that helpful, we have playlists of entire courses at the channel right here and the latest video over here. Thank you so much for watching, and I will see you in the next video.